Welcome to the course on an introduction to information theory. So we will continue our discussion on block to variable length coding, and in this lecture we are going to talk about what are the bounds on optimal code length for block to variable length coding. So to get to those bounds, we will define what do we mean by a rooted tree with probability, and then we will derive the bounds on optimal code word length, and next we will talk about a prefix free code which is known as Shannon-Fano codes. So just to refresh your memory, basically we were considering this problem. We had a message source denoted by u, which is a k-ary random variable, so it takes k different possible values, and we want to encode this source into code words z, which are of variable length, and z denotes the length of the code word z, and expected value of w gives us a measure of average code word length. So we have a list of code words corresponding to these u1, u2, u3, uk, and what we are interested is in average code word length being as small as possible. So what is the smallest value of expected value of w that we can have, and that's a measure of goodness of our source compression algorithm. So to get a bound on this, we will require some results and some lemmas and some proofs. So we will build up those results, and then we will derive the expression for lower bound on expected value of w. So we will define what is meant by a rooted tree with probability. So by a rooted tree with probability, we mean it is a finite rooted tree with probability assigned to each vertices. Now how do we assign these probabilities? This is as follows. The root is assigned probability 1, and probability of every node is the sum of probabilities of the nodes and the leaves at depth 1 in the subtree stemming from this intermediate node. So if you have consider a binary tree. So this is a root node, right? This will have probability 1, and at any node, let's say at any node w, you can just draw. So let's say we are considering this node at depth 1. So its probability will be given by probability of this node and probability of this node. That's what we meant when we say probability of every node is the sum of probabilities of the nodes and leaves at depth 1 from the subtree stemming from this intermediate node. So you look at any node here, you look at nodes and leaves at depth 1 from this node. So in this example, this is this node and this node. So the probability of this particular node is nothing but probability of at this node plus probability at this node. Similarly, what's the probability at this particular node? That is given by probability of this leaf plus probability of this leaf. So this is how we construct our rooted tree with probability. Now we are going to prove a lemma which is calling as path length lemma. So in a rooted tree with probability, the average depth of the leaf is equal to sum of probabilities of all the nodes including the root node. So what we are saying is the average depth of the leaves in a rooted tree with probability is equal to sum of probabilities of all the nodes including the root node. So let us prove this. So the probability of each node is nothing but sum of probabilities of the leaves in the subtree stemming from that particular node. Now a leaf which is at depth d will appear in d nodes on the path from root to the leaf. So what do I mean? Again, I take an example of a binary tree. Let's just take an example. Let's say these are my leaves. So these are the nodes at depth 1. These are the nodes. This is a node at depth 1 and these leaves are at depth 2. This is depth 1. These are nodes at depth 2. These are the leaves at depth 2. This is a node at depth 3. This is a leaf at depth 3. And these are the leaves at depth 4. Now what I am saying is a leaf at depth d appears in d nodes from the path to root to the leaf. So let's look at, so this is my root node, right? So if I look at path, let's look at this particular leaf. This particular leaf is at depth 1, 2, 3, 4. This leaf is at depth 4 from the root. Now how many times, now we know the probability of each node is sum of probabilities of the leaves stemming from the subtree stemming from that particular node. So probability of this particular node is nothing but probability of this leaf plus probability of this leaf. Correct? Similarly, what is the probability of this node? This is this probability plus this probability. Now please note that a leaf at depth d appears in d nodes on the path from leaf to the node. So probability of occurrence of this leaf, this appears here, right? This appears here, this appears here, and this appears here. So the contribution of the probability of occurrence of this leaf, this is appearing in the probability of this node. Now this probability of this node is affecting the probability of this node. So this probability will also affect this. Now this probability is affecting the computation of probability of this node. So this probability will also appear here. So you can see that if a leaf is at depth d, it is going to appear at d nodes. Its probability is going to appear at d nodes from the path from root to the leaf. So the sum of probabilities of the nodes equal to sum of product of each leaf's probability and its depth, which is precisely the average depth of the leaves. Now again go back to the example that we had here. So what we are seeing here is, note that this leaf is at depth 4, correct? And if we add up the probabilities of all nodes where this leaf is appearing, so this particular root node and this other 3 nodes, you will notice that contribution of this leaf is appearing at these 4 nodes. So essentially the contribution of this leaf to the overall sum of the probabilities will be 4 times the probability of occurrence of this leaf. So this is what I am saying. The sum of probabilities of the nodes is equal to sum of product of each leaf probability and its depth. So you can see that each leaf will appear in the sum equal to the depth of its leaf. So then if we do the sum of probabilities of these all the nodes including the root node, what we will get is basically we will get the average depth of the leaves in the tree. Take this example. Now, what is the sum of probabilities of the nodes including the root node? This is probability is 1, and what is this probability? The sum of probabilities of these two nodes. So this probability is 0.7. So sum of probabilities of all the nodes including the root node is 1.7. Now what does path length lemma says? The path length lemma says that this is the average depth of the leaves. And where are the leaves? There are 2 leaves at depth 1, and there are 2 leaves at depth 2. Now what is the average depth of the leaves? This is 1 into 0.1 plus 1 into 0.2 plus 2 into 0.3 plus 2 into 0.4, and this is equal to 0.1, 0.3, 0.9, and this is 1.7. This is precisely the number which is given by path length lemma. And you can see this particular node appears only once in the summation, and which is the depth of the leaf. This particular node appears only once in the summation. This particular node appears twice. It appears in this probability of this node, and it is also appearing in the probability of this node. Similarly, this particular node, it appears in the sum of probabilities of this particular node as well as root node, and which is precisely the depth of this leaf. So you can see from the path length lemma, by summing up the probabilities of all the nodes including the root node, we can find out the average depth of leaves. Now let us define a rooted tree with T leaves whose probabilities are P1, P2, P3, Pt. Then we define leaf entropy as minus Pi log Pi sum over all i's. So this is how we define leaf entropy. Similarly, we can define what is known as branching entropy. So suppose Qi1, Qi2, Qil are the probabilities of the nodes and leaves at the end of Li branches that stem outward from a node whose probability is Pi. Then the branching entropy is given by this expression, where Qij by Pi is the conditional probability of choosing the jth of these branches, given that you are at a particular node whose probability is Pi. So graphically let's have a look. So let us consider a binary tree. So these are the leaves. Let's say their probabilities P1, P2, P3, P4. Then this leaf probability is given by minus P1 log of P1 minus P2 log of P2 minus P3 log of P3 and minus P4 log of P4. That will be my leaf probability. Now if we want to compute the branch probability, let's just take, let's say, this node. Okay, and let us say that probability of this node is capital Pi. Okay, now there are 2 branches leaving from this node. Let's say the probability of choosing this branch is, this probability is this probability is Qi1 and this probability is Qi2. Then Qi1 by P1 is the probability of choosing this branch given I am at this particular node, and Qi2 by Pi is the probability of choosing this branch given I am at this node whose probability is Pi. Then the branching probability is basically given by minus Qi1 by Pi log of Qi1 by Pi minus Qi2 by Pi log of Qi2 by Pi. So that's my branching entropy. So I define two terms. One is leaf entropy, which is the entropy of the leaves, and other is branching entropy. So this is computed at each nodes whose probability of occurrence is Pi, and this is the probability of choosing any of these L branches which is stemming from this node whose probability is Pi. So let us take this example. In this case, the leaf probabilities are 0.1, 0.2, 0.3 and 0.4. So the leaf entropy in this case is given by 1.846 bits. Similarly, we can compute the branching entropy. We can compute the branching entropy here at this node, or we can compute the branching entropy at this particular node. If we compute the branching entropy of this particular node, which I am denoting as h of 1, then what are the branching probabilities of selecting each of these branch? Probability of selecting this branch is 0.1 by 1, this is 0.2 by 1, and this is 0.7 by 1. So the branching entropy for this particular node is given by this expression. Similarly, I can compute the branching entropy at this node, which I am denoting by h2. Now the probability of selecting this branch is 0.3 by 0.7, and similarly the probability of choosing this is 0.4 by 0.7. Then my branching entropy is given by this expression. Okay. Now once we have defined this leaf entropy and branching entropy, let's prove a theorem which we call as leaf entropy theorem. So the leaf entropy theorem says that the leaf entropy of a rooted tree with probability is equal to sum over all nodes including the root node of the branching entropy of that node weighted by the node probability. So this leaf entropy theorem relates leaf entropy to the branching entropy, and it says the leaf entropy is nothing but branching entropy at node I multiplied by the probability of occurrence of that node I, and this summation over all the nodes including the root node. That's my leaf entropy theorem. Let's try to prove this result. So by definition, we know that sum of probabilities at a particular node, so the probability of a node is nothing but sum of probabilities of its leaves or nodes at depth 1 from that particular node. So if you are, let's say, interested in finding the probability of this node, this is nothing but probability of this node plus probability of this node. Okay. So if you have LRE branches, you have this relation. So that's what I am saying, that this follows from the definition of rooted tree with probability, that probability of a node in this rooted tree is nothing but probability of nodes and leaves at depth 1 from that particular node. Now next look at this this term log of Qij by Pi. So in the branching entropy, if you recall the definition of branching entropy, you can see here you have this term of the form log of Qij by Pi. So if you look at this term log of Qij by Pi, this will be log of Qij minus log of Pi. Now from the definition of branching entropy, if I multiply this by Pi, what I get is Pi Hi is given by this expression. Okay. Now what is this Pi? Pi is the probability of that particular node. And what are these Qij's? Qij's are the probabilities of nodes and leaves stemming from that particular node at depth 1. So if you have a tree like this, and let's say I am looking at this particular node, then Pi is the occurrence of probability of this node, where Qi1 and Qi2 are these two. So these in the red are the probability at these nodes is my Qij's, whereas in green what I have is my probability of Pi. Okay. So note that in this Pi Hi product there are two terms which are coming in. One contribution due to probability of this node, which is a positive contribution. Second contribution is coming due to the nodes and leaves at depth 1, which is a negative contribution. So let's look at these terms further. So if you have a non-root kth node, it will contribute a sum corresponding to pk log pk to this sum which I just now mentioned. So if you have a non-kth root, there will be one contribution from due to the probability at the node, which is pk log pk, and the same node will contribute minus pk log pk to the term, because if you consider a non-root node, let's say you consider this node, this is a non-root node, right? So if I do this summation Pi Hi at this particular node, the contribution of this Pi would be this positive here. However, the same node is for this particular node, for this particular root node, this is another node at depth 1. So this Pi is actually Qij for this particular node, right? If I compute Pi Hi for this particular node, this Pi is giving me a positive contribution, which is Pi log Pi. Okay, it's giving me a contribution which is Pi log Pi, and the same node is acting as Qij for this particular node. So then this will give me a minus pk log pk contribution. So each of the nodes which is not a root node will give a pk log pk contribution when this summation is done over that particular node, and it will give me a minus pk log pk contribution corresponding to summation which is taken at one node before that particular node. So the net contribution of any kth non-root node will be 0. What about root? So if you look at root, what is the contribution of the root? Now this root will contribute Pi log Pi, where Pi is 1 to the sum. So that contribution is also 0. So the contribution of a root node is also 0. So what we have shown is, to this summation Pi Hi, summation over all nodes including root node, contribution of the root node is nil, contribution of a non-root node is also, net contribution of a non-root node is also 0. So then what is the only contribution left? Only contribution left is contribution of the leaves. So if you have trees of the form this, and if you are looking at, let's say, some of probabilities at this particular node. Then since these are leaves, they will contribute minus Qij log Qij term corresponding to the probabilities of these particular nodes. So the net contribution to this summation Pi Hi sum over all the nodes including the root node, the total contribution will be just the contribution of the leaves, and this is nothing but the leaf entropy that we have defined. Hence we have proved that this summation Pi Hi sum over all the nodes including the root node is nothing but given by leaf entropy. So this is an important result because we are going to make use of this result to compute bounds on the size of lower bound on the block 2 variable length code. Okay. So now what is leaf entropy? If we are assigning each of our code words to these leaves, the uncertainty in the source u is nothing but leaf entropy. And what is branch entropy? Since there are d branches stemming from each node, so we know from the property of discrete random variable that the entropy cannot be more than log of number of possibilities, and here the number of possibilities is d. So the branching entropy is upper bounded by log of d, and this equality happens when each of the branches are equally likely to happen. So then, invoking the leaf entropy theorem, we can write that because leaf entropy theorem says that leaf entropy is equal to summation of Pi Hi, where summation is taken over all the nodes including the root nodes. So this is our leaf entropy, right? And branching entropy we upper bound by log of d. So then this summation Pi Hi, because we are upper bounding this by log d, we can take it out. So what is left is summation of Pi over all the nodes including the root node. Now what is this quantity? From the path length lemma, we know this is the expected depth of the leaves. And what are leaves? Leaves are my code words. So this is the expected code word length, average code word length. This follows from the path length lemma. So I plug this one in here. What I get here is a lower bound on average code word length. So the average code word length should be at least equal to uncertainty u divided by log of d. Okay. So you can see using this leaf entropy theorem, we have arrived at a lower bound on average code word length for this block 2 variable length coding scheme. Now finally, let us talk about some practical prefix free coding techniques. So we will start with Shannon-Fano prefix free code. So in Shannon-Fano prefix free code, the code word lengths are given by this. So it's minus log of d of probability of occurrence of ui. So in other words, the code word length is inversely proportional to the probability of occurrence. So if a code word is occurring more frequently, it will be assigned a smaller code word length. If the particular occurrence of u is happening with less frequently, it will be assigned a larger code word length. Now to verify whether a prefix free code exists which has code word length given by wi, what do we need to do first? We need to first check whether Kraft's inequality is satisfied. So this is what we are going to do. We are going to check that if we choose wi in this particular way, will Kraft inequality be satisfied. So what does Kraft inequality says? So if u is a carry random variable, then d raised to power minus wi sum over all these k's should be less than equal to 1. So let us see whether Shannon-Fano code satisfies the condition for prefix free code. So this we can write as, now note that this is a ceil function. So this minus log of PUI might be some real number, so we round it off to the nearest larger number. So here we are doing minus of wi, which is integer smallest integer basically, which is bigger than this quantity. So if we remove this ceil function, so we are raising it by a smaller quantity, and this is minus of that, so then this will be greater than equal to this. Now this can be written as summation over I equal to k of PUI, and this is nothing but equal to 1. So what we have shown is, if we choose our code word length in this particular fashion, then Kraft's inequality will be satisfied. Hence this will be a prefix free code. So this ensures that Shannon-Fano code is a prefix free code for the choice of wi that we have chosen. Now we know that a ceil function can be upper bounded and lower bounded like this. So x is less than equal to ceil of x is less than x plus 1, and so from this so wi is given by this expression. So if we plug that in, we can write from this expression that wi is less than minus log of PUI by log d plus 1, and if we multiply both sides by, so if we multiply both sides by PUI and sum over all, we sum this over all i's, then this would wi PUI sum over all i's, that would be expected code word length, and minus PUI log PUI sum over all I, that is the entropy function log of d, and summation of PUI sum over all i's would give me 1. So what I will get is a simple upper bound on expected code word length. So average code word length of an optimal DRE prefix free code satisfies this relationship. So expected code word length is lower bounded by this quantity, and it can be upper bounded by this quantity. And of course this equality on the left hand side will only happen if the probability of each of these values of ui is some negative power of d, and in that case the Kraft inequality will be satisfied with equality. Now Shannon-Fano code also satisfies this particular bound. Now let us take a simple example of Shannon-Fano coding. So we have a Fourier random variable, a random variable which takes 4 different values, u1, u2, u3, u4, and their respective probabilities given here. So u1 occurs with probability 0.4, u2 happens with probability 0.3, u3 happens with probability 0.2, and u4 happens with probability 0.1. Now according to Shannon-Fano coding, the code word length is given by log of 1 by pi and ceil function of that. So the code word length corresponding to I equal to 1 is then given by this. Similarly, we can find out the code word lengths for other 3 UIs. So what we have is now we know the code word lengths of our prefix free code. Now if we know the code word length, we know from the algorithm that we talked about earlier how to map these code words of length W1, W2, Wk into a prefix free code. And the way we do it is we draw a full DRE tree of length equal to maximum of W1, W2, W3, W4. In this case that's 4. And then we arrange these code word lengths in the ascending order. So we'll basically arrange them like this. And then we start with the first code word, prune the tree at depth equal to from the root equal to W1. We do the same thing for W2, W3, W4, and that's how we are able to map each of these code words of length W1, W2, W3, W4 into a DRE tree, and that's how we can get a prefix free code. So you can see here I've already pruned, so this is my tree of depth maximum 4, length 4, and I've already pruned it, and you can see, so this is corresponding to UI, code word corresponding to U1, this is code word corresponding to U2 of length W2, this is of length W1, this is of code word corresponding to U3 of length W3, and this is code word corresponding to U4 of length W4. You can just again we arrived at this by first creating a full DRE tree of depth 4, and then we start pruning the tree at W1 equal to 2. So you can see the depth here is 2. So what was coming out from this node, we have pruned it. Similarly W2 was 2, so we considered a node at depth 2, and then we pruned the tree beyond that. We followed the same process for W3, which is at depth 3, and similarly for W4, which is at depth 4. Now you can see clearly this is not an optimal coding. Why? For example, this particular code word which is at depth 4, we could have easily brought in here, which is of depth 2, which would have reduced our expected code word length. So with this we will conclude this discussion on bounds on optimal code word length and Shannon-Fano coding. In the next lecture we will talk about optimal prefix free coding, which is known as Huffman coding. So we'll first talk about what are the conditions that needs to be satisfied for the code to be optimal. Thank you.